Welcome in this video about mixed circuits, where we determine a strategy of how we can solve circuits that are not purely parallel but also not purely series circuits. This one, for instance, has several resistances in the circuit, but you cannot say that it is a purely series circuit or a purely parallel circuit. In order to solve this, we are going to have to simplify this circuit by adding certain resistances together and replacing them with a replacement resistor, and try to simplify your circuit this way. How do we start? Well, first of all, we want to simplify this. So there's nothing changing about your voltage source or anything, but you're going to have to add 2 or possibly more circuits together to try and create a new circuit, one that is easier, by replacing some of the resistances with a replacement resistance. The prime candidate to add together in this case would be these two. If we consider these two together, they form a perfectly normal series circuit if we just ignore the rest. So if we want to do this, we can take our circuit and add these two together. What do? Well, we still create our parallel circuit at point A, as you would, but instead of having 2 individual resistances together of 400 and 600 ohms, we can just make this a single resistance of 1000 ohms. Why can we do this? Well, they are in series to one another, so in series you just add the resistances together in this case. We haven't touched the bottom one here, resistance 3, that one remains at 250 ohms in this case. And seeing as we haven't changed anything about this resistance either, this one remains at 600. There we go, and that is our first simplification of the circuit. Of course, your voltage source remains at 25 volts. Next, we need to select another 2 resistances that we can add together, who are in a pure in a pure series or parallel circuit if you just ignore one of the other ones. A good example would be these two. In this case, they form a perfectly parallel circuit in this case. These two. 1250 ohms. Meaning we are going to try to simplify our circuit even more. We will be adding 1 replacement resistor here, which is that parallel circuit between 1000 and 250 ohms. If we do that, it will just be cleanly in series with our last resistance of 600 ohms. Now, how much is this going to be? Well, you have to add 1 1000th plus 1 250th, meaning 1 divided by 1000 plus 4 divided by 1000. That is to say, that would be 1 divided by your new resistance. Now, let's call this resistance our double apostrophe in this case, because this isn't the total resistance of the whole network, it's just a replacement resistance we are going to be adding to this circuit. Meaning it is 5 1000th, or the total resistance is, or that replacement resistance is in this case 1000 divided by 5, or 200 ohms in this case. In other words, that replacement resistor is 250 ohms. Sorry, 200, of course. 200 ohms. Which is the parallel circuit between this one of 1000 and this one of 250 ohms. Meaning the last simplification we can do is just add these two together, and it would be its most basic circuit you can get. This would be a series circuit. It's not hard to calculate. It would be one resistance of 800 ohms connected to a voltage source of still 25 volts in this case. In other words, we have simplified this mixed circuit all the way down to being a single resistance. The total resistance of this entire circuit is 800 ohms. Why do we need this? Well, this is essentially the same as that step 1 in our previous video, the one where you had to determine your total resistance. Why do you do this? Well, then you can start calculating the total current that your system is going to draw. The current equals your voltage divided by resistance. Now, in order to make it all work, you need your total current, you need your total voltage, and your total resistance. If we add our calculator to this, we have 25 volts in this case. We divide it by our 800 ohms of resistance, and we end up with 0.03125 amps. In this case, let me just double check. Yep. Meaning there's going to be that many amps leaving the circuit in this case. If we have analyzed this, this is where we're going to take or trace our steps back. We're going to go back into the simplification network, and we're going to start adding the numbers wherever we can. What does that mean? Well, we still have our 25 volts in our voltage source, and the amount of current that is going to start at the voltage source is still going to be the 0.3125 amps. Now, when we look at this second to last simplification, this is a series circuit, meaning I can copy paste one of my numbers, my voltage number or my current number, to these resistances, even if they are virtual ones. And in the case of a series circuit, it's the amperage that you can copy paste, meaning doesn't matter if it's the replacement resistance, that virtual resistance, or the real one, they both get this much amperage through them. After having copy-pasted this, we can use Ohm's law to fill in the missing number of those two. In this case, we can calculate for our 600 ohms resistance how much voltage is going to be in there. We namely take our current and we multiply it by resistance. In this case, it means 18.75 volts out of the 25 will be going to that 600 ohms resistance here. How much is that 200 ohms resistance going to be receiving? Well, again, we take our current and we multiply that by our resistance, and that will be the remaining 6.25 volts. And now is this second to last simplification completely solved. These numbers for this fourth resistance, they're not going to change because we haven't touched those. Those still remain the same when we go to our second, or rather our first simplification. The only one that we have changed is the green replacement resistor is now the original 2 we have. And in this case, the green resistance replaced a parallel circuit. In a parallel circuit, you can copy-paste the voltage, meaning the top one will be getting 6.25 volts, and the bottom one will also be getting 6.25 volts in this case. Right? The last one we need to calculate is the current for each of these. How do you calculate current? Well, you take your voltage, 6.25 volts, and you divide it by the resistance that it's going through, meaning only 0.00625 amps will be going through this resistance. If we check the bottom one, we take our voltage, we divide it by its resistance, 250 ohms, and you end up with 0.025 amps going to the bottom one. You can ask yourself, does this make sense? Well, if I take this amperage and I add the amperage from the top, I end up with my total amperage again. So this makes perfect sense. Now, this was a simplification of my original start. In the original start, we replaced this red one. Remember, all the rest can just be copy-pasted. There's no difference there because we haven't made any changes to it. It remains 18.75 volts for this one. The currents also remain the same. To save a bit of time, I'm not going to be writing them down. But the one that I will be writing down is the one we can copy-paste from our virtual resistance, the replacement resistance, to the original ones. It used to replace this red resistance, used to replace a series circuit, meaning I can copy, in this case, the amperage. And I do this for both resistance 1 and resistance 2. Having done that, I can calculate how the voltage, how that 6.25 volts will divide between those two. I use my Ohm's law. I multiply my current with my resistance, and it tells me that this one will get 2.5 volts. The other one is, again, the current multiplied by the resistance, 3.75 volts. Does this make sense? Well, yes. If I take my 3.75 volts and I add the 2.5 volts from the other resistance, I'm back to having my 6.25 volts in this top branch. And that means the entire circuit is essentially solved. For every single resistance, I know how much voltage it will get and what amperage of current will run through it in this case. So it takes a while to solve one of these questions, but it's perfectly doable. The key is in simplifying the whole things in steps and then working out step by step until you have completely solved the puzzle. Now, there are some more exercises in our book. Normally, you should be able to do exercises 1, 2, and also 6 and 7. This is a good one to practice what we have just done as well. So good luck with those exercises, and I will see you in the next video.